Hello class. So in this video, we'll continue on section 6.2. In the previous video, we talked about the inverse of the Laplace transform. So we talked about how, since the Laplace transform is a function, we can ask about its inverse. Now, we gave an example about how, so where's the example? Yeah, so we gave an example about how functions don't necessarily have inverses, right? So we gave an example of f of x equals x squared, right? Since this function is an invertible, it's possible for the problem f inverse of something in the range to have more than one answer, right? We don't want that. We want there to be exactly one answer. Right? So what's one thing we can do? We can restrict the domain of the function into a domain in which it is invertible, meaning that it passes the horizontal line test. The same thing works for the Laplace transform. We want this question to have a unique solution. If f of s is a function in the range of the Laplace transform, when are we sure that the inverse of this function, or whatever is mapped to it, is unique? There's only one thing mapped to it. Right? And we saw that the solution is if we restrict the domain of the Laplace transform as a function, just as we did with the function x squared, to functions that are continuous, and again, this is the smaller domain because we usually consider piecewise continuous, right, for which the Laplace transform exists. Right, I didn't write exists here. Then the Laplace transform is invertible, satisfies the horizontal line test, meaning that this question has a unique solution. For every f of s, it should be the range. Sorry. And again, these are things that if I were in class, I could just correct really easy. Okay, let's correct it now for any f of s in the range. Okay. Right, now we saw an example of this, of how we use it, and then we extended this theorem 1, right, into adding these extra things. Right? Since all of these functions are continuous, the Laplace inverse of the functions of s is going to be unique. Then we also talked about how the Laplace transform and its inverse are both linear. Right? Meaning that you can separate sums and you can move constants multiplying functions outside of the Laplace inverse. So let's do an example of using this theorem. So find the following. Find the Laplace inverse of 1 over s squared plus 7. So what do? Let's go to our table, right? Is there a function that we know that is continuous and that is mapped to this thing? Okay, so let's go to our table. Okay, this looks like a constant over s squared plus 7. Okay, so let's see something that looks like that. Okay, both sine and cosine look something like this, right? Because there's a constant up in front, right, k in the numerator, and s squared plus k squared in the denominator. That looks very similar to this thing here, 1 over s squared plus 7. And of course, it's not the same thing, but it looks pretty close. So let me write those here so we have them on hand. So the Laplace transform of sine of kt is, so let me see, I don't have it memorized. So k over s squared plus k squared. Okay. And the Laplace transform of cosine of kt, is s over s squared plus k squared. Okay. Remember that k is a constant. So what can we do? If we can somehow rewrite the inside here to look like this or like this, then we would be done. Okay. Now, notice one thing here. S in this case is not a constant. S is a variable, right? This is a function of s. Okay, so s is a variable, meaning that s is not a constant. We can't move it outside of the Laplace inverse. But any other number, as long as it's not s, we can. So this is what we're going to do. I think it's going to be sine because, again, I don't see how we can move in an s in front without messing up what's going on. Again, we cannot move s's outside, but we can move k's outside. So let's try to rewrite 1 over s squared plus 7 as something that looks like k over s squared plus k squared. Well, first of all, if k is square root of 7, then k squared equals 7. right? So it seems like our k would be square root of 7. Now, what else do I need? So if k is square root of 7, then what I want is I want a square root of 7 in the numerator instead of a 7. So what I'm going to do is I'm going to multiply top and bottom by square root of 7. And then we have this extra, let me write it in the front. Right? And then we have this extra 1 over square root of 7, right, hanging out. And again, you can do this because we're just multiplying by 1. And this is exactly the same as this. Now, let's see what happens if we take the Laplace inverse of this. So the Laplace inverse of 1 over s squared plus 7 is the same as the Laplace inverse of 1 over square root of 7 times square root of 7 over s squared plus 7. 1 over square root of 7 is a constant, right? So let's move it outside. So we move the 1 over square root of 7 outside. We're left with square root of 7 over s squared plus 7. And this has exactly the form k over s squared plus k squared. So we know that this came from sine of kt. In our case, k is square root of 7, right? So this is just 1 over square root of 7 times sine of kt, k is square root of 7, t. And that's the answer. So here you're already seeing how we need to use linearity. Right? 1 over s squared plus 7 didn't have the correct form of the common functions that we're working with in theorem 6. So we somehow had to write it, and this is part A, we somehow had to write it as something that had the right form. Right? So we saw that it looks like either sine or cosine. Since s is not a constant, we cannot move it outside of the Laplace inverse. So let's better not work with that one. So we worked with the Laplace transform of sine of kt. So we tried to get it in the form k over s squared plus k squared. So if k equals square root of 7, multiply by top and bottom by square root of 7, move the constant outside, and we were done. And again, since this function is continuous, we know that this is the only solution. So that is part A. Now let's do part B. Okay, so B, and let me write it here again so we can have it readily available. Negative 2s plus 6 over s squared plus 4. Right, we're looking for the Laplace transform of this. Again, our goal is going to be to make this look like the form of one of our common functions. Right? So we can easily evaluate the Laplace inverse. Okay, so we have a sum in here, right? So we can separate it into the sums, right? Because L inverse is linear, or the Laplace inverse transform is linear. So this is negative 2s over s squared plus 4 plus Laplace inverse of s over s squared plus 4. Okay. We can move any constants outside, again by linearity. So let's move the negative 2 outside of this one. And here, let's move out the 6. And now let's try to tackle each of these Laplace transforms. Well, I think the first one already has the right form, s over s squared plus 4. That looks exactly like the form of cosine of kt, right? S over s squared plus k squared. So what would k be in our case? Well, if k is square root of 2, if k is 2, then 2 squared is 4, right? So this first part is just negative 2 times cosine of k equals 2t. Now for this one here, again, it's similar to the first one we did in the previous example, right? 1 over s squared plus 7. This one is 1 over s squared plus 4. So it's the same idea. It seems that it looks like the sine, right? The Laplace transform of sine of kt. We just have to put it in the right form. So here, if we let k be equal to 2, as before, then k squared equals 4, right? So what do? We rewrite the inside. So we write this as 6 times plus inverse of 2 over s squared plus 4 times 1 over 2. Right? So we multiply by 1. Move the constant 1 over 2 outside, and left with 6 over 3 times the Laplace inverse of 2 over s squared plus 4. And this has the right form. Right? This is sine of 2t, which equals 6 over 3 is 2, so 2 times sine of 2t. Put everything together, we had a sum of 2 terms, which we found separately. So in total, the Laplace inverse of the original thing is given by the sum of these 2 terms. So negative 2 cosine 2t plus 2 sine 2t. Again, we had to use linearity now for 2 things, to move constants out and to separate the sums. But this is basically how you use the Laplace inverse, right? And how you use the linearity property. Right? So again, we're almost there. We're almost to the point in which we can talk about or describe how we can use the Laplace transform to simplify differential equations. Okay? But before that, we're going to have to talk about the last thing, right? How to take the Laplace transform of a derivative. Okay? So let's talk about that in the next video.